In the last lecture, we explored the topic of molecular vibrations. In particular, we looked at the vibrations of the fictitious molecule that we called Triangulin. This is a molecule made out of three identical atoms and is shaped like an equilateral triangle when it is in equilibrium. For simplicity, we also assume that the atoms making up the molecule are confined to move in two dimensions. So we investigated the nature of the motion of the atoms under these constraints and also under the conditions of small departure from the equilibrium configuration. From the viewpoint of the standard theory of small oscillations, this problem is, in the ultimate analysis, that of the diagonalization of a 6x6 matrix, the so-called force constant matrix, curly F. This is a symmetric matrix whose elements are the second derivatives of the potential energy with respect to the mass-weighted coordinates. These are coordinates in which square root of mass has been absorbed so that the kinetic energy term can be just written down as a sum of the squared velocities with an extra half factor. Now, the important fact here is that curly F commutes with all the symmetry transformations of the equilateral triangle. That is, it commutes with d of g for all small g belonging into the group S3. So, in this case, of course, d of g represents the action of the group element small g on the space of molecular vibrations. And this actually helps greatly in simplifying the problem at hand. Now, the representation of the symmetry group S3 furnished by the molecular vibrations happens to be a reducible one. In fact, the reduction is pretty standard and we worked it out in the last class. It turns out that this representation is actually a direct sum of one copy of the representation A1, the identity representation, another copy of the one-dimensional representation A2, the so-called pseudo-scalar representation in which all the rotations are represented by the number +1 and all the reflections by the number -1. In addition, it also has two copies of the two-dimensional irrep, which we have called curly E. This is the standard 2D vector representation for the group S3. That is just something which tells you how 2D vectors behave under the action of the elements of the group S3. Now, as we have argued before, this reduction greatly helps us in understanding the different normal modes of vibration of this particular molecule. However, there are three body modes which have no restoring force associated with them among these normal modes. They are the two translational modes along the x and the y axis respectively, and a rotation of the molecule in its own plane. Now, it so happens that the rotational mode transforms according to the representation which is marked A2, whereas the two translational modes transform according to the vector 2D representation, which is sort of obvious. As a result, if you take these modes away, what we are left with are the purely vibrational modes, and hence the vibrational modes furnish a representation which is a direct sum of a single identity representation and a two-dimensional representation d of E. A consequence of this would be that we expect there to be one normal mode which is invariant under each and every one of the group operations, and in addition to this, you have two more vibrational modes which belong to the representation d curly E, and these two modes have to be of the same normal frequency for the simple reason that you should be able to transform one mode into another, or at least into their linear combinations, by applying the group operations. Now, today what we are going to do is we are going to look at these issues in some more detail. And in order to make things a bit more concrete, let us talk about a specific model. This is a toy model of the triangulin molecule, where we imagine that the molecule is made up of three balls which are identical, connected by three identical and of course equally long springs, so that in their unstretched position the molecule is in the form of an equilateral triangle. Now, because we are using springs here, we know exactly how much the the forces will be when you displace the atoms, or in this case the balls, from their equilibrium position. It will of course depend on good old Hooke's law. However, the calculation here is slightly complicated by the fact that the displacement of the two ends of the spring caused by the two balls moving away from their equilibrium position are not always in line with the spring. So the geometry actually gets a bit complicated. So for a spring with an equilibrium length L0, so what we are doing here is we are taking a look at a particular spring. The elongation, when the two ends are displaced by R2 and R1 respectively, is easily seen to be the new length minus, of course, the old length. The new length is nothing but the length of this vector L0 n hat, which was the original vector joining the two ends, plus R2 minus R1. You take the modulus of that gives you the stretched length of the spring. Subtract L0 from that. This is the elongation which the spring has. Of course, the changed length may very well be less than L0 depending on R2 and R1, in which case, of course, instead of an elongation, this would be a contraction. A negative elongation is a contraction, so we should not really have to worry very much about that. In any case, we are going to use this in the potential energy formula, where you need the square of the contraction or the elongation, so it doesn't really matter whether this is a contraction or an elongation at this stage. What we are calculating, of course, is an elongation, at least formally. Now this thing can be rewritten obviously by taking the L0 out of the bracket, that is dividing the vector in whose magnitude you are taking by L0 to get n hat plus delta R by L0, where delta R of course is R2 minus R1. Now this is actually not such a very simple expression, because the length of the vector n hat plus delta R by L0, as you all know, can be written down as a square root obviously of the square of its length, and the square of its length is given by this quantity. N plus delta R by L0 whole square is of course a dot product of n plus delta R by L0 with itself, and that gives you L0 times square root of 1 plus twice n dot delta R by L0 plus another term which is delta R whole square by L0 square. And because we are assuming that the balls are displaced only by a tiny amount compared to the overall scale of the figure, we are going to assume that delta R by L0 whole square can be neglected. So this is the expression for the elongation. And now what we can always do is use binomial theorem to get a good estimate of this, at least estimate which is correct up to linear order in delta R. And that is immediately seen to be simply delta R dot n hat. So the elongation, at least to first order in delta R, when you displace the two endpoints of a spring by R2 and R1 respectively, is actually given by R2 minus R1 dot n hat, where n hat is a unit vector in the direction of the spring. Making use of these elongations, we can easily construct a formula for the potential energy of this triangulin molecule, or our ball and spring model of the triangulin molecule, at least for small displacements. What we are going to do is simply retain up to quadratic order in the displacements, and that is exactly what the small oscillations approximation is all about. The expression depends, of course, on all the coordinates x1, x2 up to x6, which are the components of displacement of the three atoms, or three balls in this case. And this is what the expression looks like. Now this may look like a pretty complicated expression, but let me break it up for you. Half m omega 0 square is of course half times the spring constant k, which is an overall factor which is there for every one of the springs. Remember, the springs are identical, so they all have the same k. Now if you look at the horizontal spring, the displacement R2 minus R1 for that particular situation is of course the displacement of the two lower balls, and that has components x5 minus x3 in the horizontal direction and x6 minus x4 in the vertical direction. This has to be dotted with the unit vector along the lower spring, which is entirely in the horizontal direction. So this gives you x5 minus x3. And then you square it to get the elongation squared. Now if you look at any one of the other springs, let's say the left hand inclined one, the two endpoints have been displaced by different amounts, and the horizontal component of delta r here is x1 minus x3 and the vertical component is x2 minus x4. This has to be dotted with the unit vector in the direction of the spring, which is half in the horizontal direction and root 3 by 2 in the vertical direction. And this dot product is exactly what is sitting in the second term in the square bracket there. The third line is actually the potential energy due to the other spring, the inclined one on the right, where the two endpoints have relative displacement of with components x1 minus x5 and x2 minus x6 respectively. And the unit vector that we have used here, the unit vector along the unstretched equilibrium direction of the spring, has components minus half and root 3 by 2. This is what gives me this final expression. Now if you expand out the entire thing, you get this rather formidable looking expression for the potential energy of the spring ball system. And let me point out that this is still not an exact expression. This is a quadratic approximation to the exact expression. The quadratic approximation looks formidable enough, but it's rather easy to figure out where these terms come from. All you have to do essentially is go back to your previous equation and then just expand it out and use the standard a plus b whole square kind of formulas that we need. Since the Fij's are just the del qi del qj of this vqi, it is very easy to actually write down the matrix form for the curly f, force constant matrix. In fact, you can even just read off the coefficients if you pay attention to this. And the curly f matrix turns out to be this particular 6 by 6 matrix. So even for this very simple toy spring and ball problem, what we are supposed to do in the end is diagonalize this particular 6 by 6 matrix, and this does not look like an easy matrix to diagonalize at all. So what we are going to now do is go back to the more general triangulin molecule and use the power of group theory to try to simplify the solution of this as much as possible. What exactly are we looking for here? Well, we are trying to look for a way to simplify the calculation of the eigenvectors as much as possible, so that if we can easily calculate the eigenvectors of this matrix, it will be very easy for us to then determine the different eigenvalues. Group theory will give us a way to determine what the eigenvectors are going to be, or at least give us a big push in the direction of finding out these eigenvectors. So let us now go back to the general theory. As the general theory has told us, the space of molecular vibrations provides the representation for my symmetry group S3, and this representation is reducible. It breaks up into dA1 direct sum with dA2 direct sum with 2 copies of dE. So this means that if we could choose our basis properly, each and every one of the representation matrices dG would end up having a structure which looks like this. A 1 by 1 block marked in a darker color in the top corner, standing for A1. The pink circle stands for the other 1 by 1 block, which is dA2, and the two sets of blue circles of 4 stand in for the 2DE representation matrices. So each and every one of the DGs will take this form, provided of course we have chosen the correct basis. And if we actually use this basis, curly F, which commutes with each and every one of the DGs, will have a form which is dictated by the Wigner-Eckhart theorem. And let me just remind you of what the form is going to be. It is essentially going to be something like the one which is shown on the right here. So you will have a non-zero element corresponding to A1, the top corner. Because there is only one copy of A1, this particular basis vector will not mix with any one of the other basis vectors by the action of curly F. And so curly F will have a column and a row, the first row and the first column, which contains only one non-zero element, which is the 1-1th element. Similarly, because of A2 being the only copy of the representation occurring in this particular reduction, the 2-2 element will be the only non-zero element in the second row and the second column. However, the two copies of the two-dimensional representation TE, which are present in this reduction, means that what we are going to get is a 4x4 non-trivial matrix in curly F. However, there are going to be other connections between the matrix elements as dictated by the Wigner-Eckhart theorem. According to the Wigner-Eckhart theorem, the 3-3 and the 4-4 matrix elements would have to be the same. Similarly, the 5-5 and the 6-6 matrix elements would have to be the same. The 3-5 element is now a matrix element of curly F between two basis vectors which both transform like the first vector in a basis for the DE representation. Since they both transform similarly, there is a possibility of a non-zero matrix element for curly F there. So that element can be non-zero, but not just the 3-5 element. The 4-6 element could also be non-zero. And again, according to the Wigner-Eckhart theorem, this must be the same as the 3-5 element. Similarly, on the other side, because curly F is symmetric, you would end up with two other non-zero elements, the 5-3 and the 6-4. So this is the general situation for any curly F matrix which commutes with each and every one of the D of G's. Of course, our curly F matrix, the one we figured out a while ago, does not have this structure at all. It has lots and lots of non-zero elements spread out all over the place. What has to be borne in mind, however, is that this is the particular form curly F will take in the spatial basis where all the D of G's become block diagonal. Or, in other words, if you use a basis in which the basis vectors actually form bases for the invariant subspaces which your original space of all molecular vibrations break up into. If you look at the curly F matrix, you can immediately say some things about its eigenvectors. It is obvious that E1, the basis vector which spans the space which transforms under the representation A1, is an eigenvector of curly F. The fact that the first row and the first column has only one non-zero element, the 1-1 element, is a sure sign of that. Similarly, E2, the basis vector which transforms like A2, will also be an eigenvector of curly F. I must apologize for a change of nomenclature here. When I say E1, E2, E3, E4, E5 and E6 now, I do not mean the original basis vectors that we used to describe displacements of each of the individual corners of the molecule from their equilibrium positions, but rather the basis vectors that will block diagonalize our DGs. So this set of E1, E2, etc. vectors are different from the ones we started out with. I hope this will not lead to any confusion. Or the 4x4 block spanning the 3rd, 4th, 5th and 6th columns of these matrix tells us at first glance that E3, E4, E5 and E6 would mix together under the action of curly F, and therefore the other eigenvectors will have to be found out by solving this 4x4 eigenvalue problem of finding out those particular combinations of E3, E4, E5 and E6 which actually are eigenvectors of curly F. However, the special constraints imposed by the Wigner-Eckhart theorem makes the problem even easier. Let me remind you that what we had seen earlier is this. If instead of using this particular order of writing down the basis vectors E3, E4, E5 and E6, we had instead used the order E3, E5, E4 and E6, then curly F would take a form in which this 4x4 block would break up into two smaller 2x2 blocks, in fact two identical 2x2 blocks. So ultimately what we really get is E3 and E5 will mix together to give you two eigenvectors. E4 and E6 will mix together in an identical fashion with identical coefficients to give you two more eigenvectors. And of course, because the two blocks are identical, you're going to end up with the same eigenvalues for both. So that is the general scenario. Here there is something more that we can say simply because we know that one of the 2x2 blocks in the representations for DG correspond to translations. The other 2x2 block corresponds to basis vectors which execute vibrations. So E3, for example, could be a vibrational mode, whereas E5 could be a translation along the x-axis. Now, if the off-diagonal elements in curly F were really non-zero, what would have happened is that we would have to solve a non-trivial 2x2 eigenvalue problem to find out the actual eigenvectors, and the eigenvectors would be a combination of E3 and E5 and some other combination of E4 and E6. Now, the important point is E3 denotes a vibration, E5 denotes a translation. A linear combination of the two can never denote a vibration because in a vibration the center of mass will not move, whereas in a translation the center of mass will move. So the combination that will give us a vibration, a normal mode, cannot be a non-trivial combination of E3 and E5. It has to be E3 and E3 alone. This is what tells us that the off-diagonal terms here, the 3-5, the 4-6, 5-3, 6-4, these terms in the matrix curly F has to vanish. What a textbook usually says about this is translations do not mix with vibrations, and therefore, although Wigner-Eckhart theorem does allow you to have non-zero values for the 3-5 matrix element, because they essentially would have mixed a translation with a vibration, such a matrix element has to be zero. So, in our problem, things are even simpler than what it looks like at first glance. All the off-diagonal terms are really zero, so curly F will be a perfectly diagonal matrix with 3 zero eigenvalues and 3 non-zero eigenvalues. But remember, this will happen only if you choose the basis which block diagonalizes all the DGs. But how do we find out such a basis? The answer, of course, lies in the projection operators that we had spent quite some time on in a previous lecture. Let me remind you that the projection operators were basically defined as follows. The ith diagonal projection operator for the alpha-th irrep, P alpha II, was defined to be a weighted sum of the operators which represented the group in this particular reducible representation. The weighting factors are actually complex conjugates of the ith element of the alpha-th irreps matrix representatives. Each operator that is acting on your vectors in the current representation, you multiply them by components which you take from the irreducible representation matrices. So, in order to work with the projection operators, it is not enough just to know the characters for the irreps or the character for the representation that you are reducing. You need to know either the operators which furnish the reducible representation that you are trying to reduce, or the corresponding matrix equivalence, and you need to know the matrix elements, at least the diagonal matrix elements, for the irreducible representation matrices. Without that piece of information, this calculation simply cannot be done. Now for our symmetry group S3, we have 4 diagonal projection operators. We have 3 irreps, 2 of them one-dimensional, which gives rise to 1 diagonal projection operator each, and the 2-dimensional irrep curly E gives us 2 diagonal projection operators. And in order to figure out what these operators are, you will need to remember what the matrices, irreducible representation matrices for these representations actually are. You can look back at these representations that we discussed earlier, or you may work them out all over again. In either case, the simplest one of the projection operators is of course the projection operator which projects to the identity representation, and there it's easy to see that all the coefficients d alpha g are simply going to be 1. So PA1 is simply going to be the sum of all the linear operators representing the different group elements. I'm talking about the operator version for this. Of course, if you wanted to talk about the matrix version, it will replace the LE, LA, LB, LC, etc. by the corresponding matrices, the 6x6 representation matrices in our reducible representation. PA2 is similarly pretty easy to figure out. A2, remember, is a one-dimensional representation where the rotations are all represented by the number 1 and the reflections are represented by -1. And so PA2 simply turns out to be LE minus LA minus LB minus LC plus LD plus LF. P curly E, there are 2 of them, P curly E11 and P curly E22. And in order to figure out what they are, you will have to look back at the representation matrices for the 2-dimensional irreducible representation. If you do that, you will find that these projection operators are also not too difficult. P curly E11 turns out to be LE minus LA plus half LB plus half LC minus half LD minus half LF. And P curly E22 is very similar, except that there is a difference in some of the signs. So these are the 4 projection operators that we can apply on arbitrary vectors in our 6-dimensional space, and the resulting vector is guaranteed to be one of the basis vectors. In fact, if you apply PA1 on an arbitrary vector, the result might of course vanish if your original vector has no component in the direction of the basis vector which spans this particular invariant subspace where the elements are invariant under all the group operations. But if you get a non-zero result, you are going to get a vector which is in this one-dimensional space. On the other hand, if you apply PA2 on a vector, the result, if non-zero, has to be something which transforms under the representation A2. Now the situation is slightly more complicated for P curly E11 and P curly E22. The reason behind that being the fact that there are 2 copies of these 2 irreps in our reducible representation. So when P curly E11 goes and acts on an arbitrary vector, the result may of course be 0, but if it is non-zero, it is going to be a vector which transforms under the group operation like the first vector in this 2-dimensional representation. But now it can be a linear combination of both of the 2 first vectors in the 2 irreps. If you remember the nomenclature that we used a while ago, P curly E11 can actually give us a sum of E3 and E5, or rather a linear combination of E3 and E5, and P curly E22 would in general give me a linear combination of E4 and E6. Now, what makes our life a bit easier here is that we know that one of these possibilities is a translation along the x-axis for, let's say, E5 and along the y-axis for E6. So if you want to figure out exactly what E3 or E4 is, all I have to do is to make sure that you take away any piece which talks about the translation from the resulting vector. So if you apply P curly 1, 1 on an arbitrary vector, you would in general get a linear combination of E3 and E5. But if you manage to make the translation go away, which is pretty easy to do. Remember, under a translation, the center of mass doesn't move. So if you can subtract a translation which keeps the center of mass fixed, you are going to end up with just the vibration or just a vector which is proportional to E3. A similar thing can be done with E4. So without further ado, let us try to take a look at what these projection operators do when they act on arbitrary vectors. And while we can write down column matrices for the input vectors and apply matrix versions of these linear operators on them to figure out exactly what happens to them, it is perhaps much more interesting and definitely much more instructive to take a look at what happens to an arbitrary vector under the geometrical action of these operators. After all, these operators, LE, LA, LB, LC, etc., do certain simple geometric operations on our space, so it should be easy and definitely more satisfying to use geometry to understand what the projection operators really do. Let us begin then with the action of PA1. I should also perhaps point out that according to our standard notation, this should have a pair of indices 1 and 1 stuck to it, but since there is only one value which the index can take, this being a one-dimensional irrep, I have decided to omit that extra piece of notation. And the same goes for PA2. Now PA1, as we have just figured out, is LE plus LA plus LB plus LC plus LD plus LF. And let's start with an arbitrary vector in our 6-dimensional vector space and apply each of these operations one after the other on it, add them all together and see what our final result of PA1 acting on our vector V is going to be. So for our vector V, we can start with any vector in the 6-dimensional space, but let us say we start with something rather simple. A vector V which essentially is a multiple of our original E1. That is, only the first atom has been displaced to the right. Every other atom, the other two, are fixed at their equilibrium position. Now what happens when we apply the operator PA1 on this? That is our question right now. And for this, we apply each of the operators LE, LA, etc. in succession. So LE acting on this vector V is of course the same as the vector V, LE being the identity operation. LA is a reflection along the vertical line, along this particular median. So when you apply LA on V, V simply flips over. So this is what LAV is. What about LBV? B is a reflection along this line. So when you apply LB, this particular vector gets reflected, but not only that, the atom moves from this corner to this corner. So this is what LBV is going to be. I would urge you to actually take down pen and paper and draw this thing out yourself. It is much easier to convince yourself of the truth of all that I'm saying if you actually were to do it on your own. LCV, reflection along this particular line, will move this atom here. It will also reflect this vector in this line, so it will make it point somewhat like this. So this is what LCV is going to be. Now comes LD, which is a 120-degree rotation, which brings this point here, carrying the vector with it, of course, and the vector also will turn through by 120 degrees, which means instead of pointing horizontally, it will end up pointing in this direction. So this is LDV. Finally, LFV, the last of the operations, when that acts on the vector V, firstly the atom moves to 240 degrees, so ends up in this corner, and the vector turns around to 240 degrees and ends up pointing in this direction. So this is what LFV is. So now that we have all of our resulting vectors, we can just simply add them together to find what PA1 acting on V is. Let me just remind you that here we actually have a 6-dimensional vector space, but it is really 3 vector spaces stuck together. So what happens is the vectors on the first atom gets added to each other, vectors on the second atom gets added to each other, vectors on the third atom gets added to each other. So these are essentially 3 separate vector spaces. In technical terms, this is really what is called a vector bundle, but we are not going to use such advanced terminology here. But if you do this, it's pretty obvious what's going to happen. LEV and LAV are going to cancel, LBV and LFV are going to cancel, LCV and LDV are going to cancel, and you're going to land up with 0. So our first action of PA1 on a vector V turned out to be a damn squib. It did not really yield the result that we wanted. If we had obtained a non-zero vector from this, we would have been sure that that non-zero vector is a vector which spans the one-dimensional invariant subspace which carries the representation A1. Or in other words, it would be a vector which is invariant under the action of each and every one of the group elements. But that did not work out here, because when you applied PA1 on V, all you landed up with was 0. Which simply means that the vector I started out with did not have any component in the particular basis direction that we are looking for, which is why when we tried to project into that basis direction, we ended up with 0. What do we do in such a situation? Well, the answer is very simple. You just started with one particular vector out of the infinitely many possible vectors you could have picked in the 6-dimensional space that you are in. So what if you have got a 0 when PA1 acts on this particular vector V? Just try it with another vector. As simple as that. So let us try once again, and this time let us use a vector V, which is again one which talks about the first atom being displaced, and only that one, but being displaced vertically instead of horizontally, as we considered earlier. So this is the vector V that we are talking about. Let's apply our LE, LA, etc. on this vector V and see what happens. LEV, of course, trivially is V itself. LAV is actually the same as V, simply because when you reflect along the vertical median, which is the reflection A, the vector V stays the same. It simply doesn't change. So that's all you have. LBV does something non-trivial. First of all, it moves the atom from here to here, and if you're pointing up, the resulting reflected vector points in this direction. Actually, it might be easier for you to understand the direction of this vector simply by considering the fact that this median, the median through this vector, which is the direction in which this vector V really is, under the reflection about the other median becomes the third median. So this vector is really a vector directed at the median of this triangle, along the median of this triangle, which passes through this particular point. By the same token, LCV essentially produces a vector going through this other median. The vertical median being reflected in this median gives rise to the third median, and this is what LCV points towards. Now comes LDV, and it is easy to see that LDV and LCV are one and the same. And LFV, no surprises there, is the same as LBV. So now comes the time of putting them all together all over again, adding them all together. But when we do that, I get a non-zero final result. This is the vector which spans our one-dimensional invariant subspace. It's a vector where each atom is displaced along the median by equal amounts. If you started with a vector V of a particular length, let's say unit length, then each of these three displacements would be of 2 units length, simply because they get contributions from 2 of the vectors each. And next step, of course, would be to write down the components for this, because that's what we are going to need to do further calculations. And the components are easy enough to write down. Since we are going to normalize the vector in the end, I don't really have to worry about the factor of 2. If I just had 3 vectors of length 1 each, the components would obviously be 0 and 1 for the first vector. Those are the first 2 elements in the column vector here. E3, E4 will be minus root 3 by 2 and minus half. Again, easy enough to figure out. And finally, root 3 by 2 and minus half will be the components in the direction of E5 and E6. Now, since this vector, if you took a norm squared, you would get 3. That's easy because each of the unit vectors give you 1. So you end up with 1 square plus 1 square plus 1 square. To normalize this to unit length, you will need to put in a further factor of 1 by root 3 outside. So this is a normalized vector which spans our one-dimensional invariant eigenspace. In fact, it is pretty easy to see that this vector is invariant under the action of each and every one of the group operations. The symmetry which this particular configuration has is sort of staring you right in the face. It's easy to see that if you were to reflect it along any one of the 3 medians, or turn it through either 120 or 240 degrees, or do nothing at all to it, the configuration will stay exactly the same. In fact, at least for this particular representation, you could have perhaps done away with the projection operator and figured out that this is what the invariant basis vector would look like, simply from the fact that the basis vector is invariant under the action of all the group elements for this particular representation. What kind of molecular vibration does this talk about? It essentially gives you a vibration where each of the 3 atoms move out equally. And of course, they do not only move out, they also move in equally. And so the whole thing expands and contracts while staying an equilateral triangle throughout. So this is what is called a breathing mode of vibration. It looks like it's a breathing organism which expands and contracts as it breathes in and breathes out. Let us now move on to PA2. As I have been saying before, the representation A2 in this particular context is relevant for rotations. We have stated that the rotations live in the representation A2, which is why when we talked about the vibrational modes only, we left out the one single occurrence of the A2 representation in the reduction of the overall 6 by 6 representation. While it is easy enough to see that rotations do actually transform under the representation A2, let us take a look at what PA2 has to say about that. And for that, what we will do is we will apply PA2 on an arbitrary vector V. In this case, let us choose the vector V to be the first choice that we had made before, a horizontal displacement for the atom at the top. So it's pretty easy to figure out what this is going to be. I will quickly go through the steps. LEV is of course the same as V. LAV is opposite, but minus LAV is what you need here. So minus LAV is in the same direction. Minus LBV is opposite what LBV was for the horizontal V, of course. Let me just remind you that this is B. So LBV will be a vector stuck here pointing in this direction. And minus LBV will of course be in the opposite direction. Similarly, minus LCV, it's pretty easy to figure out that this is what minus LCV is. LDV turns out to be exactly in the same direction as minus LCV. Should not come as a surprise. Remember when we took our horizontal vector as our starting vector, LCV and LDV cancelled. So minus LCV and LDV must be in the same direction. And similarly, LFV will be in the same direction as minus LBV. If you add all of these vectors together, you obviously get vectors which are 2 units long at each one of the vertices. And the special thing about these vectors are that they are all going to be perpendicular to the line joining the center of the triangle to that particular vertex. That obviously is what you would see for displacements in a rotation. So this is your final setup, and it is easy to see now that when PA2 acts on a vector V, what the resulting basis vector for the invariant subspace which carries the representation A2 is going to be is nothing but a rotation. And this is of course what we have already used earlier when we said that the A2 representation stands for rotations, and so you can drop that when you are talking of vibrations only. The vector corresponding to this can be written down just as easily, so I'm not going to explain all the individual steps behind writing down this particular vector, but it is a straightforward enough calculation to do. You can easily see that, for example, that the first two components have to be 1 and 0. Of course, you have to normalize ultimately by 1 by root 3. The other components are also easy enough to figure out. Let us turn now to the two-dimensional irrep curly E. And here, of course, we have two projection operators, at least two diagonal projection operators, P curly E11 and P curly E22. P curly E11, as we had already seen a while ago, is given by this particular expression. And once again, what we are going to do is we are going to start with an arbitrary vector and apply P curly E11 on that. The vector we are going to start off with is again the simple choice that we have made several times now, a vector which is pointing towards E1 and has only an E1 component, all other components are 0. This, of course, is a starting off point. Then we get Lev, exactly as the V itself, minus Lav, as we have seen just now, has to be in the same direction as Lev, in fact equal to it. And half LBV, we have already figured out earlier what LBV is. This is just half of that, so it's just half as long. Half LCV, similarly, in this direction. Same direction as LCV, but half as long. Minus half LDV, 120 degree rotated. The top atom moves to the left corner and turns through 120 degrees with an additional 180 degrees because of the minus sign and scales by half. Ends up being exactly the same as half LCV, and minus half LFV similarly works out to be exactly the same as half LBV. So when you add all of them together, this is the total result of P curly E11 acting on V. A vector of length 2 in the horizontal direction on the top atom and two other vectors of length 1 each. Remember, you have two individual pieces which had lengths half each, giving us lengths 1 each along these directions indicated. And you can easily write down the components corresponding to that in a column vector. Now, the important point to bear in mind is, as I have said a while ago, P curly E11 acting on a vector is going to give you a vector which transforms like the first vector in an irrep transforming like curly E. Which is fine, but here in this particular representation of ours, we have two copies of the curly E representation. As a result, this particular vector that we have obtained would usually end up not being one of the basis vectors for the corresponding invariant subspaces, but a sum or rather a linear combination of these two basis vectors. As I have explained before, one of these basis vectors happens to be a translation, so it is pretty easy to be able to figure out its effect and in fact pretty easy to compensate for it. If you add up the three vectors here, that is the three individual displacements of the three atoms, the resulting thing is pretty straightforward. You get a vector which is 3 units long in the horizontal direction. Note that here we are no longer talking about the vectors in this 6-dimensional space. We are going to treat R1, R2, R3 as vectors in the same space and add them together using the ordinary rules of vector addition. This is how you are going to get the displacement of the center of mass. If you add them together, the lower two vectors add up to give you a vector of 1 in the horizontal direction. Adding all three together gives you 3 unit long vector in the horizontal direction. But that has to be divided by 3. Remember, there are 3 masses to get the center of mass's displacement. So this particular configuration corresponds to a vibrational mode and a center of mass displacement which is exactly 1 unit long in the horizontal direction. So in order to figure out the vibrational piece, you have to subtract from this particular translational mode, which is simply that you have to take away from each one of the atoms, or rather the displacements of each one of the atoms, a vector which is 1 unit long in the horizontal direction. So the top vector simply ends up being 1 unit long. In fact, all three vectors end up being 1 unit long, and this is the final vibrational mode that transforms like the first vector of this 2D irreducible representation. The corresponding column vector is pretty easy to figure out. All you have to do is subtract 1, 0, 1, 0, 1, 0 from the previous vector, and you're going to end up with this one. Or you could, of course, figure out the components directly from the geometry of the problem. Now, some of you might just be worried about what might happen if we apply this P curly E11 on some other initial vector rather than pick up on our vector V. Well, in this particular situation, we already know that we must get back essentially the same answer, and the reason for that is for the following. Although we do have two copies of this particular irrep here, one of those irreps stand for translations, and we have already figured out how to get rid of the translations. So there is only one vibrational mode left, and so if we start with any other arbitrary vector, what P curly E11 might do is that it might kill the vector completely, yielding 0, or it might end up giving me a pure translation, or, and this is the final possibility, it would again give you a combination of the vibration and the translation, but if you took the translation away, just as I did for this particular case, I would get back the same vibrational mode as the one we have found right now. Just to see whether that really happens, let's apply this projection operator P curly E11 on a different vector. In this case, I have chosen a vector which points along one of the springs. So, along one of the sides of the triangle. Here, it's pretty easy to figure out geometrically what will happen to this under the action of each and every one of the group operations. This is LEV, same as V, of course. LAV would be reflected horizontally, but this is minus LAV, so it will be down along the side as shown. Half of LBV will be in the same direction as LBV would have been along another side, but half as long. Half LCV, again along another side, half as long, minus half LDV as shown, and minus half LFV as shown. It does not take a lot of effort to actually add all of these together. After all these vectors in each case are of equal length, making an angle of 120 degrees with each other. So the resulting sum is going to be a vector of the same length, making an angle 60 degrees with the original vectors, bisecting the two vectors at each vertex, and you are going to end up with a vector which looks like this. This may look like a different vector from the one that we had obtained before, but let me remind you that this is once again a sum of the vibrational mode and the translational mode, and if you take away the translational mode, which in this case would involve a vector of half unit length along the horizontal direction, you are going to end up with a vector which looks like this. And this vector is, of course, exactly the same as the vibrational mode basis vector that we had found out a while ago. So in a sense, this particular effort was a bit of a waste because it doesn't give us anything new, but at least it should confirm for you that this method P curly E11 does really give me one of the vibrational basis vectors. Let us now move on to a more non-trivial thing, that is, in fact the final non-trivial thing, figuring out the vibrational mode which transforms like the second component of this curly E representation. That is, the result of P curly E22 acting on an arbitrary vector. The vector which we will start with is a vector which is vertically upwards. Why not? I could have taken any vector. I've just taken one vector, which is a vector which points vertically up and constitutes of a displacement only of one of the atoms. And then I keep on applying LE, LA, minus half LB and so on. And I will just quickly show you what happens. It should be pretty easy for you to figure out all the results yourselves. And when you add all of these 6 vectors together, remembering once again to add vectors at a given vertex to each other, you're going to end up with something which looks like this. Once again, pretty easy to figure out what the components are going to be. However, this again is not a pure vibration, it's a combination of a vibration and a translation, and it is very easy once again to figure out that the translation is 1 unit long along the vertical direction here. So if you take that away, that is subtract a vertical vector 1 unit long from each of the 3 displacements, you're going to end up with a mode which looks like this. So once again, it should be pretty easy for you to imagine what the molecule will look like when vibrating like this. One vertex will go up and the other 2 ends will sort of squeeze. We will try to see what the vibration actually looks like through a computer simulation soon. Now that we have figured out what the vibrational modes look like, turn to our toy ball and spring model. This has a particular curly f which commutes with each one of the d of g's, and hence which takes up a very simple form when you choose our quote-unquote correct basis vectors. These are the basis vectors which describe the various vibrational modes as well as the translational and rotational modes. Let me point out that the nature of the basis vectors for each of these modes is the same irrespective of the precise form of curly f, as long as your molecule has the correct symmetries. So group theory will tell you exactly what the normal modes look like. What group theory will not do is tell you what the eigenfrequencies are, because those frequencies depends on the particulars of the curly f matrix. And that of course can differ from system to system despite the fact that the systems may all have the same symmetries. What we are going to do now will depend specifically on this particular curly f matrix that we had worked out for the toy ball and spring model. Some of the basic features though will still stay the same. So let us be clear about what group theory can do and what it cannot do. It can tell you a lot about what the nature of the vibrations will be like, but what it cannot tell you is what the precise eigenvalues or eigenfrequencies will be. For that, you need specifically to take a look at a specific force constant matrix. Let us now start with the force constant matrix for our toy ball and spring model and try to figure out what the normal frequencies corresponding to each one of these oscillation modes are going to be. As we had stressed earlier, group theory helps us to find out the eigenvectors of curly f, or at least goes a long way towards figuring out the eigenvectors of curly f. And once we have found the eigenvectors, finding the rest of the information for the normal modes is easy. The rest of the information, of course, means just the normal frequencies. The displacement modes are already fixed by the eigenvectors. So let us see that in action for our toy model. First, let us check the trivial modes. Translation. Well, we already knew that this has to be a normal mode, and this should really be a normal mode without any restoring force. And that is very easy to check by simply applying our curly f matrix on the column vector describing this transformation. The normalized version, of course, is 1 by root 3, 1, 0, 1, 0, 1, 0. You can forget about the 1 by root 3. That's just an overall normalizing factor. That will have no bearing on the potential eigenvalues. If you carry out the multiplication of the force constant matrix and this simple 1, 0, 1, 0, 1, 0 column vector, you are going to end up with a column vector full of zeros, as you can easily check. And this confirms for us that this corresponds to an eigenvector with an eigenvalue 0. Or, in physical terms, this corresponds to a displacement which has no restoring force whatsoever. So that is a translation along the x direction. Well, a translation along the y direction is also equally trivial. The vector, once you normalize it, is 1 by root 3, 0, 1, 0, 1, 0, 1. I will just multiply the curly f matrix by 0, 1, 0, 1, 0, 1 and end up once again a very simple calculation. The result is going to be 0, 0, 0, 0, 0, 0. So, once again, this confirms that a translation along the y direction is a mode which is an eigenmode but corresponds to the eigenvalue 0, so has no restoring force associated with it. So you could say this is a mode with 0 frequency. Let us next consider another body mode which is not so trivial, the rotation mode, which, as we had figured out, is one in which each of the atoms move perpendicularly to the line joining the atom with the center of the triangle, or in this case the ball with the center of the triangle. The corresponding vector is one we had already figured out, and multiplying the force constant matrix and this particular vector, you are going to get the null vector once again. All this is rather simple and straightforward. What is not so simple and straightforward, and what is not trivial at all, is the result that we are going to get when we apply the same considerations to the vibrational modes. So this is our first vibrational mode. This, remember, is a mode which is invariant under all the group operations and hence transforms like the irreducible representation A1. And in order to figure out the corresponding frequency, all you have to do is multiply curly f and the corresponding displacement vectors, which we had already figured out before. The product is straightforward. You can easily carry out the multiplication. In fact, since you know this is an eigenvector, you don't even need to figure out all the components. You figure out the component corresponding to any one of the non-zero elements in the original vector. You're going to figure out what the eigenvalues are. So the eigenvalue works out to be 3 omega 0 square. So this particular mode of oscillation, this breathing mode as we described it, corresponds to a frequency of root over 3 omega 0. So not only has group theory told us what kind of vibrational mode this particular molecule can have, actually it's helped a lot in figuring out what the corresponding frequency is. Let me once again stress that you could not possibly find out the particular frequency here without knowing the force constant matrix, but the fact that group theory actually helps you figure out the eigenvector makes finding out the eigenvalue very, very easily once the force constant matrix is given. In addition to this, we have two other normal modes, two vibrational normal modes which transform among each other like the irrep curly E, and we already expect them to have the same frequency. Let us just verify whether that is the case and also find out the corresponding frequency. We know the vibrational mode. One of them happens to be this one, and multiplying curly f by this particular displacement vector immediately yields the corresponding angular frequency as square root of 3 omega 0 square by 2. So root over 3 by 2 times omega 0. What about the other vibrational mode which belongs to the same irrep? We already expect it to have exactly the same frequency, but it's easy to check since we already know what the corresponding vector is. So note that I have taken the purely vibrational mode because that is an eigenvector of curly f. And this particular purely vibrational mode corresponding to this column vector gives rise to exactly the same eigenvalue of 3 omega 0 square by 2 and hence exactly the same frequency. So now what we have figured out in the end is that for our toy ball and spring model, the eigenfrequencies are root 3 omega 0 and root 3 by 2 omega 0. The root 3 by 2 omega 0 normal frequency is twofold degenerate. There are two independent vibrational modes, each with this frequency. Note that for a general triangulin molecule, the eigenvectors will of course stay the same, and this twofold degeneracy for one of the normal frequencies will still persist. The precise value of the normal frequency of course depends on the details of the potential energy. or the details of whatever model we are using for the triangulin molecule. Let me finish with a simple demonstration of what the vibrations actually look like. For this, I am going to use a program that I wrote using NumPy and Matplotlib. The methods that were used were essentially Runge-Kutta integration, something which you have all learned about. So you should be able to write code like this yourself pretty easily. In fact, I would invite all of you to try your hand at this. Try writing down your own code to simulate the motion of a molecule like this. Let's just see what the molecule's vibration essentially looks like. So we start the simulation, and this is what the triangulin molecule would vibrate like. I've just drawn the three edges of the molecule. Let me point out that this oscillation that you see is purely vibratory. There is no translation or rotation, as you can perhaps notice. But what you can also notice is that this is not periodic at all. The motion is completely aperiodic. And the reason for that is that the initial conditions we have started this motion with has several normal modes excited. In fact, all three vibrational modes have been excited here. And because the three normal modes do not have commensurate frequencies, two of them do, but one of them has a frequency which is square root of 2 times the other, you can easily figure out that the overall motion is not going to be simple harmonic or not going to be periodic. So let us now take a look at what happens if we change the initial conditions so that we excite only one normal mode. For this, I will just edit my file. I am not going to go through the details of all the steps here. It's a slightly lengthy program, primarily because of all these bells and whistles you need to draw the molecule. But actually, it's very easy to see that all we have done here is we have three initial conditions. xx1, xx2, xx3 are simply the amplitudes of the three normal modes. Here we started with, as you can see, the values 0.3, 0.1 and 0.4, which means all the three normal modes have been excited. Instead of that, if I just started with the first normal mode excited, which means I changed the amplitude of the other two normal modes by 0, we should be able to see the breathing mode. So let's run the simulation again and see what happens. So now you can see that the molecule is expanding and contracting as a whole, breathing as I said, and in fact you can perhaps even time the oscillations. Or at least you can even take out a stopwatch and time how long it takes for this to complete 10 complete oscillations or whatever. Of course, because I'm actually running a simulation, I can easily figure out the time period of oscillation just from the program itself. But you might pretend that you are really doing an experiment with a real molecule here. So you see the breathing mode, the thing going in and out. Now let us try to take a look at the other modes. So if I replace the first mode's amplitude by 0 and this mode's amplitude by 3, 0.3. 0.3 is just a number I chose arbitrarily so that this looks decent. Let's try the simulation. This is the second normal mode that we found out, one in which one vertex moves outwards, the other ones move along the line. And this is what the actual motion looks like there. You perhaps can also figure out that this vibration is somewhat slower than the previous vibration, and that is consistent with the fact that this is an angular frequency which is square root of 2 times less. And finally what we will do is we will take a look at the other normal mode that we have. Same frequency as this one, but transforms differently. And the mode of course looks different. So for that, what we need to do is change the parameters here. Change this to 0 and this one to 0.3. When we run the simulation, this is the oscillation that we get. Note that the top atom is moving vertically up, the other two are squeezing in, just as the nature of the normal mode suggested. This is also once again a periodic oscillation, and if you were to time it carefully, you would find that this has exactly the same period as the last mode that we looked at, which is exactly what group theory told us would be the case. So we have seen the three normal modes, the breathing one and the two degenerate normal modes corresponding to the same frequency. Let me stress once again that the frequency of this particular normal mode and the previous one is less than the frequency of the breathing mode, less by a factor of square root of 2, which is what our detailed calculation with the ball and spring model had told us. As a final example, let me just show you what happens when you excite the two degenerate modes together. So we can excite them together just by giving them non-zero amplitudes. XX1, remember, is the amplitude for the breathing mode. I am keeping that as 0. Now what we have are two modes excited together, but they have the same frequency. As a result, the motion is still going to be periodic. More complicated than what we have seen so far, but definitely periodic. So let me just run the simulation, and this is what you are going to see. If you pay careful attention, you would see that the atoms are essentially executing periodic oscillations, and the frequency, you could time it, is exactly the same as the last two oscillations that you have seen. Of course, you could have started with any other two amplitude combinations. You would still get a periodic oscillation with the second frequency of root over 3 by 2 omega 0. You cannot combine this oscillation with the breathing mode and expect to get a periodic motion simply because the breathing mode has an entirely different frequency. So I am pretty sure you should all be convinced that whatever group theory told us about the nature of vibrations is being borne out by these simulations. We will have more to say about molecular vibrations in a later lecture, but for the time being, we will close this topic and move on to another application of group theory to physics in the next lecture. Bye till then.